we're ready to derive the Taylor series of a function. So we'll start by writing a function as a power series. We'll write it as a power series about the value x equals a. So the terms are x minus a squared, etc. And we have these unknown coefficients. So the idea then is to determine these unknown coefficients so that this becomes a Taylor series. So what's the main idea of a Taylor series? The main idea is that the function and all its derivatives evaluated at x equals a has to agree with the power series and all of its derivatives at x equals a. Those constraints will allow us to determine these coefficients C0, C1, etc. So let's see how that works. If we start with f of a, and we plug x equals a into the power series, the x minus a will be 0, x minus a squared is 0. So all of these terms are 0, and the only non-zero term is C0. So now we've determined C0 is equal to f of a. Okay, now we take the derivative. So the derivative of the function evaluated at x equals a, what does that give us? The derivative of C0 is 0 because it's a constant. The derivative of x minus a is just 1, so that will give us C1. And then all the other terms will still have an x minus a in them and will go to 0. So f prime of a is just C1. Let's do another one here. F double prime of a. So now we're taking the second derivative of both sides of this expression. So the second derivative of C0 is 0. The second derivative of a linear term is 0. So this term then will become a 2C2, and then the derivative of x minus a is 1. So that will be 2C2, and all the other terms will still have an x minus a will be 0. So this is 2 times C2. One more, and then we can see how to generalize. So now we take the third derivative. 0 for the constant, 0 for the linear, 0 for the quadratic. Now if we take the third derivative of this fourth term, we bring down a 3 for the first derivative, and then when we bring down a 2 for the second derivative, so 3 times 2 times C3. But 3 times 2, it's actually 3 times 2 times 1, because when we take the derivative of x minus a, we're bringing down a 1. So we should write this as 3 factorial times C3. So similarly, this 2 here is the same as 2 factorial. This 1 here is the same as 1 factorial. And this 1 here, we can define that to be 0 factorial. So now we can solve all of these coefficients for the coefficients C0, C1, C2, C3 in terms of the function and its derivative. And if we do that, we get the Taylor series. So the Taylor series for f of x is equal to f of a plus C1, which will be f prime of a times x minus a, plus f double prime of a over 2 factorial times x minus a squared, plus f triple prime of a over 3 factorial times x minus a cubed, plus ... And that's the Taylor series expansion of f of x about x equals a. Usually, we Taylor series expand functions about 0, so we might as well do this. This is the most common form. So if we take a equals 0, then we will have f of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 x cubed over 3 factorial, etc. Okay? And that's the expansion of f in a Taylor series about x equals 0. It's the most common expansion that we'll use. Okay, one of the uses of the Taylor series is in approximation. There's another form for the Taylor series that's a little bit more convenient than this one. If we write f as a function of x plus epsilon, where epsilon is some small number, then we can Taylor series this expansion about epsilon equals 0 would be f of x plus epsilon f prime of x plus epsilon squared over 2 factorial f double prime of x plus dot, dot, dot. So you can just remember this expansion. It's very similar to the usual Taylor series. And it's very simple to derive this expansion in terms of one of these forms of the Taylor series. So let's look at an example. Let's look at an approximation. So let's approximate 1 over 1 plus epsilon, where epsilon is a very small number. So what we're going to do then is look for a Taylor series of this one using this form of the Taylor series. So our f of x plus epsilon is our 1 over 1 plus epsilon. So f of here x is 1. So f of x plus epsilon at x equals 1 is equal to our 1 over 1 plus epsilon. So then we need to know what f of x is. So f of x then is just 1 over x. Right? And then the derivative is simple. The derivative is x to the minus 1, so it's minus 1 over x squared. And we evaluate these at x equals 1. So f of x at x equals 1 is 1. F prime of x at x equals 1 is minus 1. So we get our approximation 1 over 1 plus epsilon is approximately equal to 1 minus epsilon. And then if you wanted to compute the second derivative, you can get the next term in the approximation. But this linear approximation is the one that's most widely used. So let me summarize. We've derived the Taylor series for f of x about x equals a. And then we looked at what is the Taylor series when a equals 0. So then we have this final Taylor series, f of x equals f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus etc. This is really the Taylor series to remember. We will make use of this all the time in higher math courses. Finally, we showed how you can have a Taylor series of f of x plus epsilon when epsilon is small and expand this in terms of powers of epsilon. This is very useful for approximations. And I showed you how 1 over 1 plus epsilon can be approximated by 1 minus epsilon, which means a rational function approximated by a linear polynomial. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.